Hello and welcome to the chaotic pendulum. Imagine a simple pendulum. Move the bob a little from its equilibrium position and let it go. It is easy to describe its motion. It's going to move back and forth periodically. We can solve this problem and find the frequency and period of the oscillations. Even if the angle is large, the system is clearly deterministic and relatively simple to describe and predict. If you repeat the experiment again, starting with the same initial conditions or very near them, the behavior will mimic the previous one. Now think of a double pendulum. Move it from its equilibrium position and wait to see what happens. Now stop the pendulum and repeat it. Try to use the same initial conditions and observe. You will see how, after a while, the motion will be different from that of the previous experiment. The system is sensitive to the initial conditions. Even though we can describe the motion with relatively simple equations and there is no noise in it, the system is unpredictable. The system is chaotic. Small change in the initial conditions leads to a very different evolution. There are other ways of obtaining a chaotic pendulum. For example, think of an iron bob that is placed right between two identical magnets. That will give you another chaotic pendulum. Now, think of a simple pendulum with dissipation and periodic external forcing. Consider that we apply the forcing at the pivot of the pendulum as if we were forcing its rotation, the rotation of its pivot. To describe the motion of the system, we write the equation for the torque with respect to the pivot of the pendulum. We want to describe the temporal evolution of the angle theta. We have the dissipative term proportional to velocity, as usual, minus b times theta, and weight contribution in the theta direction as mg, L sine of theta, and the periodic external forcing as f naught times cosine of omega of the forcing frequency times t. This nonlinear equation is familiar and it is the same one as the forced oscillator. For small oscillations, the problem can be solved. We can find a chaotic transition and then a periodic behavior where the periodicity comes from the external forcing. But let's not stop in small oscillations. Making a normalization of the variables, we rewrite the equation as x2 dots equals to minus c times x dot minus sine of x plus f times the cosine of omega t prime. You can solve this equation numerically. Feel free to use Mathematica, MATLAB, Python, or whatever coding language you are familiar with. Then let's plot the angular position versus time. We choose the following parameters. C equals to 0.05, omega equals to 0.7, and f equals to 0.4. For these parameters, we get this periodic behavior of the angular velocity versus the normalized time, which in phase space gives this closed trajectory. But if we increase the force to 0.5, we see this a little more complicated behavior, it's still periodic though. Increasing the force to equals to 0.6, the behavior is not periodic anymore. It is chaotic. The representation in phase space is not limited to a closed trajectory, and a small change in the initial condition leads to a different trajectory, still in this shaded area. Let's talk of another system, very similar to this one, the Duffing oscillator. This is a system constituted by an oscillator in the presence of damping and a two-well potential. This means that the external force comes from a potential that shows two attractors. There is a competition between the natural oscillatory behavior of the system, damping, and the two attractors that can lead to a very rich variety of behaviors. If the energy of the system is high enough and the damping low enough, we can see how the system moves between the two wells in a periodic fashion. If friction is too high, then the energy of the system is too low. The system will be bounded to a single well and perform also periodic motion there. But in between those cases, we can go from periodicity to chaos. Let's assume we keep everything constant, but we increase the damping of the system. very low damping, as we said, the time series, so the temporal evolution of the position, is periodic. As we increase the damping, the time series gets more complicated until it becomes chaotic. The fact that the system is chaotic for a wide range of damping values doesn't mean that chaos is the same in each case. Chaoticity can be quantified, and that can be reflected in the complexity of the time series. There is a very interesting way to analyze these complex nonlinear systems. It is through Poincaré sections. Poincaré thought of a way of visualizing the dynamics in phase space by taking individual pictures of this phase space and letting a time between two consecutive pictures. So it is just an stroboscopic movie of what is going on. If we set our repetition rate to be just the frequency of the external forcing, for example, we can know where the system is every period of the forcing. Why is this interesting? Well, think of a periodic motion that has the same period as the external forcing. What would it look like on a stroboscopic movie? Yes, just a dot in phase space. Every period the system is in right the same spot. Think now of a periodic motion of period 2. Yes, then this stroboscopic movie will be 2 dots in phase space. This stroboscopic movie is what we call Poincaré section. Let's go back to the two systems we introduced before, the one with the periodic external forcing and the Duffing oscillator, with two wells. For the first case, for f equals to 0.4, we see, as expected, a single dot in Poincaré section. 3 dots for f equals to 0.5, as the system takes 3 periods to complete the closed trajectory. For f equal to 0.6, where the system is chaotic, we find the area where the system moves, but it is not periodic anymore. For the Duffing oscillator, as we increase the damping, we obtain these Poincaré sections. The system starts being periodic, but it jumps to chaos, and in the chaotic region, Poincaré sections seem similar to each other, but we can tell that they are not equal. At the end, the system returns to the periodicity when friction is so high that it cannot longer be in both wells, and it gets trapped in one of the attractors in one of the wells. I mentioned before that there is a way to quantify how chaotic one system is. That way is through the Lyapunov exponent. That is a parameter that measures the distance between two different trajectories. Let's go back to the concept of chaos. A system is chaotic when it's sensitive to the initial conditions. That means that you have one system and its time evolution follows a trajectory in phase space. If you change a tiny little bit the initial conditions, then at the beginning the trajectory will be very similar, but after a while, the trajectory will diverge from the previous one. So a little tiny change in initial conditions can lead to very different trajectories.
The man who said, "I'd rather be lucky than good," saw deeply into life. People are afraid to face how great a part of life is dependent on luck. It's scary to think so much is out of one's control. There are moments in a match when the ball hits the top of the net, and for a split second it can either go forward or fall back. With a little luck, it goes forward, and you win. Or maybe it doesn't, and you lose.
Well, one way to quantify how chaotic the system is by measuring the distance between the two trajectories, how quickly those trajectories diverge. Well, the Lyapunov exponent does exactly that. You can also think of it like, okay, let's go to the lab, let's do an experiment, let's take some data, let's see how precise I have to be measuring the initial conditions to predict, to forecast the future. If the system is very chaotic, the information I need to gather from the beginning has to be very high. If the system is not too chaotic, well, probably I can predict a little bit of the evolution, but after a while, of course, I know that that will diverge. So it's a measurement of how much information I need to know to predict the system. But even though I know a lot of information in my initial conditions, I know that sooner or later I will not be able to predict the evolution of the system. You can also think of it like, well, Taylor's expansion. So how many orders do I need to consider to see that after 1 second I still can predict the evolution? So this Lyapunov exponent is a very interesting tool. It's just a number that tells us how quickly those two trajectories diverge. If the Lyapunov exponent is positive, then the system is going to be chaotic. If the Lyapunov exponent is negative, then the system is not chaotic. The two trajectories will not diverge. Look at this graph. This graph represents the Lyapunov exponent versus the damping parameter in the case of the Duffing oscillator. Remember that system where we have an oscillator, we have damping, and we have those two wells, and the system is moving between those two wells. Well, if you remember, at the beginning the system was not chaotic, then it jumped into the chaotic region, and at the end it was not chaotic again. If you look at this plot, you will see that, okay, the Lyapunov exponent at the beginning is negative, so it's not chaotic, then it increases sharply, and then it changes a little bit, but it's still in the chaotic regime because it's still positive, and then at the end it goes to the negative region, so the system is not chaotic anymore. But if you look at what happens in the chaotic region, you see that that's going up and down, so the quantification of chaos is different as we are changing the damping, which is the control parameter in this particular experiment. Let us now find a way to calculate the Lyapunov exponent. We are wanting to measure the distance between two trajectories with very similar initial conditions. Let's consider an iterative dynamical system. Let's call delta naught, the distance in initial conditions, a value very, very small. We can always write the distance at the nth iteration as delta sub n equal to delta naught times the exponential of lambda times n, where lambda is the Lyapunov exponent, and delta n is the distance at the nth iteration. We can take logarithms of both sides of this expression and get lambda equal to 1 over n times the log of delta n over delta naught. We rewrite delta n as the difference in the nth iteration of the different trajectories. But look that this is just the definition of derivative. So lambda equals 1 over n times the natural log of the derivative of the nth iteration. But the nth iteration is just the function of the function of the function of the function of the blah blah blah. So by the chain rule of derivatives, we have that lambda can be written as 1 over n times the sum from I equals to 0 to I equals to n minus 1 of the natural log of the derivative of the function in the limit when n tends to infinite.